Hello, good morning to everyone. Can you hear me? Please.
Yes, good morning.
Well, thank you very much. I introduce myself. I'm Vittorio Di Cocco from Cassino University, and I am the chairman of this session. Welcome to the session number 13. And we have 9 presentations. For each presentation, we will use 10 minutes, around 10 minutes. I think 2 minutes for a short presentation and the rest of the time for the question and answers. So the first work is dual energy X-ray method for kidney stones and atherosclerotic plaques structural integrity characterization by Martini, Koku, Mikhail, and Funtos. Please.
Good morning.
Good morning, Martini.
May I share my screen so you can see my presentation?
Thank you.
Okay. I have a message that it's disabled, the screen sharing.
It's disabled?
Yeah, the host disabled the participant screen sharing.
Oh. The host, just a moment.
Yes.
Okay, try now.
Okay, perfect. Okay.
Okay, thank you. Thank you.
Okay, the title of our study is Dual Energy X-ray Method for Kidney Stones and Atherosclerotic Plaque Structural Integrity. We actually developed the dual energy X-ray method for the characterization of the calcific kidney and uteric stones and the atherosclerotic calcifications, since their composition is strongly related to their structural integrity. Monoenergetic and polyenergetic studies were conducted, calculating the effective calcium to phosphorus mass ratio, and the experimental evaluation followed, identified the smallest thickness at which statistically significant difference could be obtained between the different mineral types that were examined. Hydroxyapatite phantoms of 0.7, 1.5, and 3 millimeter thickness, and the equivalent thicknesses for calcium carbonate and calcium oxalate were constructed. We used a polymethyl methacrylate tank in order to simulate the torso. And in this slide, you can see the radiation conditions as they proposed by the simulation study. The experimental results of the effective calcium to phosphorus mass ratio were assessed through the two-tailed Mann-Whitney U non-parametric statistical test. And here you can see the results of our method. Statistically significant differences between all the minerals were found for thickness of 1.5 millimeters or higher, while for when hydroxyapatite was to be differentiated from calcium carbonate or calcium oxalate, the thickness was diminished to 0.7 millimeters or higher. Since hydroxyapatite and calcium oxalate are the most frequent minerals found, the proposed method can characterize the main calcium minerals and help the physicians, since the knowledge of either the kidney or uteric stones or atherosclerotic plaques calcification composition is a key factor for them. Finally, I would like to tell you that this research was co-funded by Greece and the European Union through the operational program Human Resources Development, Education and Lifelong Learning 2014 to 2020 in the context of the project Human Body Mineral Characterization using Dual Energy Method. I hope I kept the time that we had. That's it for me.
Thank you very much. And any question from the other colleagues online? Please. No one? I have just two curiosities. I see your work online, your presentation online, and I see that you used an anode, tungsten anode. In my laboratory, sometimes I often use a copper anode. Why do you use this kind of anode? Is there some problem of the wavelength of the radiation?
No, you use a tungsten anode because it's we actually use a classic X-ray tube that we use for X-rays, and we talk about the part of the thorax and the lower torso. So we believe that with the tungsten anode we have more more photons, so we can do this subtraction that we need at the end for fuel energy. Another type of tungsten, excuse me, of anode may be used for mammography. It is not that useful for us, actually.
Okay,
it works better for us.
It's a problem of hazardous too, or not for the human health using the copper radiation, I think.
Yes, yes.
And the second curiosity is how many peaks of the spectra do you consider in this in your research for each material?
Actually, what we do with the way we work for the spectra is that we try to make them as monoenergetic, pseudo-monoenergetic, actually. So we the mean energy that we use and actually the peak that we use is as smaller as we need in the band. So we somehow use a monoenergetic option. So we try from the very beginning to make them pseudo-monoenergetic, so to have a very small band.
Okay. Thank you very much.
Thank you.
And other questions from the colleagues online? No one? Thank you very much, Nikki.
Thank you.
And we move to the next presentation. The title is Assessing to the Information Content of a Non-Destructive Testing CMOS Imaging Detector.
Yes, good morning.
Good morning.
You can hear me.
Yes, clearly.
Fine. Following the outstanding previous presentation, my name is Dionysios Nardatos from the University of West Attica from Greece. Let me share. Just a moment. I'll show.
Okay.
I will proceeding pointing out some key elements of our presentation. In our study, we evaluated the novel entity X-ray detector, employing an overall image quality metric, the information capacity, that encompasses the effects of sharpness, contrast, and noise. Just a moment. Leaping directly to the results, we have the just a moment. Both the noise and resolution affect the curve shape. The curve amplitude is affected by the number of X-rays at the detector surface. That's why the higher exposure provided the higher noise equivalent quanta values. Both curves peak at the low frequency range, and this prominence is of interest in for general radiography applications. In this table, we present a comparison under matching conditions of the information capacity values between the detector under consideration and those of a similar one coupled to different scintillators. The pressure detector information capacity is higher than that with gadolinium oxysulfide. Instead, it was found lower than that of cesium iodide combination. This data show that for a given level of incident fluence, the information capacity is mainly determined by the intrinsic phosphor material properties and by the skin thickness. We move to the conclusions. The practical value of the information capacity is that it evaluates image information quantity by a single numerical value. Our results show that the information capacity values of the pressure detector are comparable to those of previously studied ones of different dimensions, coupled to various scintillators. That's for me. Thank you very much.
Thank you to you. Any questions from the colleagues, online colleagues? No one? Thank you for the kind presentation. And I would like to ask to you just an aspect of your research. You used a CMOS imaging detector. CMOS is a very good technology, changed our manner to perform some analysis in laboratory. Yes. In your study, you investigated the sensibility of the sensor mainly to external noise. For example, if the one of these external noises often is the alimentation, power alimentation, in terms of problem generating from the power supply, who must be very continuous, but we have a lot of problem of variation of the tension, electric tension on the electronic devices. Are you examine which is the variation of the signal when you use a power supplier characterized by a not so good ripple, for example?
Yes, this kind of problems are very frequent in sensitive electronics like CMOS, but also in other kind of detectors like CCDs. In fact, in our research, we use a very robust detector designed specifically for entity applications. This one is uses a power supply from the computer that you connected. We didn't have any problems. One.
So, if I catch well, you use the power supply from the PC, normal PC.
Yes, because this one is a USB connection. So
this is a good information because the noisy is very high because the power supply of the PC is sometimes often is a switching unit, and the variation of the volts tension. Well,
always switching. Yeah. But this detector makes all the signal processing very close to the chip itself.
Yeah.
So there is no interference from outside. The total signal processing is taking place in the chip, and the signal, the data are transferred via the USB cable.
Okay, thank you very much. And other questions from the audience?
Excuse me, may I ask something, Mr. Linardatos?
Please.
Mr. Linardatos, in the results slide that you showed us, we saw that the detector with the C size shows better information capacity despite its greater thickness. How is it possible?
Yes, the fact is that with cesium iodide scintillators, the thallium-doped one, is grown in a columnar fashion that resembles needles. This structure provides improved resolution despite the possibly increased thickness. It's because its column acts as a light pipe that channels the visible light to the sensor below. So that's why you have a greater value.
Thank you very much.
Other questions? No one? Oh, thank you, Dionysius, for your kind presentation. And I have to move to the next presentation. The title is Investigation of a Sulfur Melter Heating Coil as an Industrial Product, a study case on technical design and structural inspection by Prasetio, Istanto, Ciao, and Prabowo.
Yes, I am here, sir.
Please, singing.
Okay. Can I up my presentation? Can see my presentation?
Just a moment. Okay, it's aligned.
Okay.
Perfect.
Okay. Good morning. Best wishes to all of us. Please allow me, Singgiti Prastyo from Universitas 11 Maret Indonesia, represent other author to present the result of investigation of sulfur melter heating coil as an industrial product, a study case on technical design and structural inspection. Okay, the industry always innovate in developing the quality of product to achieve the desired target. One of them is a heater to heat a fluid, which one of them is heat exchanger type. The most important part of the heater is the cathode heater coil or filament fabrication of coil heater product is interesting to study, which cover design, manufacture, and machining activity. The presentation discuss the fabrication process of sulfur melter heating coil, which is carried out in one of manufacture industry. The research method is conduct a field survey to observe the design and fabrication process. Overall, production stages are divided into the design stage, which is to obtain technical illustration of the product. Material selection stage, which is to calculate and determine product material. Manufacturing stage, which is to determine the machining process of each product part. Assembly stage, which is to determine the type of joining in each product part. And finally, the structural inspection stage, which is to check the standard of fabricated product. To determine the feasibility of product result, dimensional inspection, penetrant test, full annealing, and final dimension inspection are carried out. Examination result based on dimensional inspection and penetrant test indicate that the manufactured product is following existing standard. Then the result we have done. Thank you for your attention.
Thank you very much. Some questions from the audience. No one?
Excuse me, sir.
Please?
Yes.
Please. Please, Daniel.
In your work, what are the procedures for fitting and welding?
Okay, thank you. Can my answer?
Yes.
Okay. In my work for procedure of fitting and welding are performed at the time of fitting. Welders must also consider the shrinkage due to welding. Weld or track welds that must be conducted by qualified fitters, and welding is carried out following welding procedure. VPS welding is performed using a gas welding machine, tungsten arc welding GTIW, AWS class ER70S6. Welders or welding machine operator must be selected who are qualified or certificate. Welding can only be performed if it has received permission from the quality control. If welding is done from two sets, the root pass must be good and checked by a penetrant test. And welding results are inspected by visual measurement, penetrance, and radiographs according to design requirement. Tolerance of weld result is follow. Welding phase height, bed maximum 2.4 to 3.2 millimeter, undercut maximum 0.5 millimeter, and overlap maximum 0.5 millimeter. Fitting and all welding result must comply with tolerance. And cross joint or welding meet from four direction is avoided with a distance of at least 5 times of the thickness of the used plate. Okay.
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 SB answer.
Other question? I have just a question for you. I saw your presentation online, and I saw that you used a control with penetrant methods, liquid penetrant methods. But using the inspection penetrant method, you consider only the defects involving the surfaces. In the welding zone, why didn't you use other non-destructive control like magnetic control or other ones?
Okay, because in industry can because in industry has its own standard. Standard in industry.
Okay, so just because it's a standard.
Yes.
I catch well. Thank you very much. Other questions from the audience? No one? So thank you, Siggy. And let's move to the next presentation. The title, thank you to you. The title of the next presentation is Assessment on the Design and the Structural Frame of the Automatic Thicknesses Checking Machine Validation Infinite Element Method by Zulfiqar, Prabowo, Ridwan, and Nubli.
Okay.
Please. Please. Please, Mohammed.
My screen?
Yes, perfectly.
Okay. Hello, everyone. My name is Muhammad Faizul Fikar, and I'm from Mechanical Engineering Department, Smart University, Indonesia. I'm delighted to take this opportunity and to make you a short presentation about my latest research. My research is assessment on the design and structural frame of the automatic thickness checking machine, numerical validation in FE method. Thickness measurement has an essential role in brick pad manufacture. As an example of thickness measurement usage in the industry is like in Akebono Brick Astra Indonesia under quality control department that use ultrasonic thickness gauge to measure brick pads thickness, and this gauge operated by a man to check specimen one by one. To achieve efficiency in time and manpower, this measuring method should be converted into automatic checking. And the automatic thickness checking machine use square hollow 6061 aluminum type because of its availability on the market, so that this machine can be produced without a lack of the material frame. The frame connector is needed to assemble the aluminum frame to stand rigidly, and it is made from ABS plastic. And the material properties can be seen on screen. And the loading type applied on the simulation are all distributed load on the top side of the frame and on the top side of the frame slider. The total load given on each top side is 100 Newton and divided into two brackets. Thus each bracket loaded by 50 Newton weight. And the meshing properties can be seen on screen also. And from this research, I've discovered that square hollow aluminum 6061 frame is viable for the structure. And the second, the result has von Mises maximum stress 29.86 megapascal and a minimum 2.275 times 10 power minus 5 megapascal. And the third, for this factor of safety, the maximum factor of safety is at 15 and the minimum is at 3.362. And fourth, the maximum magnitude displacement is 6.475 times 10 power minus 2 millimeter. And the last, price aspect is one of the major outlook of industrial products. And that's all from me. Thank you.
Thank you very much. Any question from the audience? No one? So, Mohammad, your work is entitled Assessment on the Design and Structural Frame of Automatic Thickness Checking Machine, Validation Infinite Element Method. And in your simulation, you discovered that the maximum stress is about 30 megapascal. Okay, it's a very low values. Where is the optimization? My opinion is that you can reduce the section in order to use much more better the properties of the materials, because the aluminum 6061 is characterized by strength upper to 270 megapascal, and you use just 30 megapascal. Where's the optimization?
Okay. In this research, the optimization is meant by the checking type, like as on screen, the thickness of the wall is just 25 millimeter and it's so thin. And the load by the machine, like the motor and the any uh, working element is just 200 Newton on top side, and it is divided by two on the right side and the left side, and the total can be 100 Newton. And it's not the optimization on the material, but the optimization on the industry. Like we need to achieve uh, the best quality in the quality control, but with the least cost efficiency, I mean the least cost and the least manpower, so that the cost of production can be minimized.
Thank you. I suppose that your external load are not the real external load. You use the just values, and then you can obtain the correct values considering that the structure is in a linear stage, because it's proportional to the internal stress is proportional to external load. Any question from the audience? No one? Thank you, Muhammad. We will move to the next presentation, and the title of the next presentation is Effect of Climate-Induced Parameters on Fracture Properties of Semi-Circular Coated Wooden Specimen under 3-point bending. Authors are Carvan, Javad, Berto, and Bertolin. Please,
yes.
Carvan.
Yes, hello.
Hello.
Can you hear me?
Yes, perfectly.
So let me start. So thank you for the introduction. My name is Purya Karman from the Norwegian University of Science and Technology and TNU. Today, on behalf of my colleagues, Professor Razavi, Berto, and Bertolin, I'm presenting a work on the effect of climate-induced parameters on fracture properties of semicircular coated wooden specimens under 3-point bending. So the main objective of this study was to somehow replicate the harsh condition of Norway and the wooden objects that undergo this type of situation, which is relative humidity and high relative humidity depending on season. So for the first 18 days, Scott fine specimens were placed inside the climate chamber at 80% relative humidity and room temperature. Then in the span of 1 day, relative humidity would drop to 30%, and the top and bottom surfaces were applied with coating, wax, 3 slices, paralloid high amount, 2 slices, low amount of paralloid with 1 slice, and finally 3 slices remained uncoated in order to be compared with the one that was kept outside of the climate chamber but inside the laboratory within the room conditioning. So 6 specimens of semicircular were produced out of each slice, 3 in the RT and 3 in the TR direction, in order to be tested by the MTS machine. 3-point bending test was performed, and the value of K1C were obtained, as you can see on the right-hand side picture, for different samples in the RT and TR direction. By analyzing this data, we found that values of K1C vary slightly in the RT and TR direction, as you can see. But for the uncoated and coated with high amount of paralloid, fracture resistance was higher in the RT direction. And finally, samples with low amount of paralloid coating had the higher fracture resistance, while those acclimatized and uncoated had the lower K1C. That's all for this brief note from me, and thank you.
Thank you very much, Furia. And I ask to the colleagues if there are some questions. No one. Okay. Furia, I have a question for you. Yes. I saw in the online your full presentation, and in your work, you discovered that the critical stress intensity factor is characterized by a slight variation in RT and TR directions. I think this is obvious because the wood is a non-isotropic material. My question is why the coated components show high values of the increment of the K1, critical K1 in 3R system?
These coated, when they applied, they kind of somehow limited the top and bottom surfaces from free movement that the standard outside or inside the climate chamber had. So it had some stickiness to these coated specimens that probably resulted in more resistance of the wood when the 3-point bending was applied, and the high values of load were critical load were obtained where these experiments were done.
So, and it's just my curiosity, because I find no information about this, but my curiosity is in the influence of the coating. How is the influence of the coating in the RT direction in terms of critical stress intensity factor? Do you investigate this or not?
The effect of coating, as in this figure shows, it increases the fracture resistance for the high and low amount of paralloid. But for the wax, it seems that it is somehow similar to the one was kept inside of the climate chamber. So in overall, the paralloid, either high or low amount, increased the critical value of K1C in our case. Especially also these were subjected to acclimatization inside the climate chamber. So that's also a factor to be considered.
Thank you very much. Thank you. And other questions from the colleagues? Oh, no one. Thank you, Purya. And we move to the next presentation for today. The title is Prediction of Ductile Fracture, Lossy of Structural Steels and Aluminum Alloys using KAEB concept and MSS criterion. The author is Professor Akai.
Hello.
Hello.
Can you hear me?
Good morning. Yes, perfectly.
Okay, let me share my screen.
Okay.
Hello, everyone. My name is Fuzuli Akçay and I work at Istanbul Technical University. My presentation covers determination of ductile fracture loci of 2 aluminum alloys and 2 structural steels. The fracture locus provides equivalent failure strain of a material for different state of stress conditions. However, to perform a series of reliable experiments to produce various state of stress conditions is challenging as well as expensive. Hence, a fracture criterion with a small number of calibration parameters is vital in order to identify a fracture locus with a minimum number of experiments. Therefore, the objective of the current study is to compare advantages and disadvantages of 2 fracture criteria involving 1 calibration parameter, a recently developed energy balance concept, abbreviated as CAB, and the maximum shear stress criterion, abbreviated as MSS. In this regard, the energy balance concept and the maximum shear stress criterion are implemented to determine the fracture loci of 2024 aluminum alloy, 6061 aluminum alloy, ASTM A572 grade 50 steel, and AISI 1045 steel. So as can be seen from the figures in the slide, majority of experimental data points are confined in between 2 fracture loci. These results suggest that mixed mode fracture appear to dominate in the majority of the experiments, and combination of tensile and shear mode fracture loci in one curve can be more convenient than presenting each of these fracture loci separately. Therefore, a hybrid model stated here in the red box is proposed in order to combine tensile mode and shear mode fracture models. The proposed hybrid model requires two calibration parameters, gamma and C cap. Here, gamma determines the contribution of shear in the fracture mode. When gamma equals to 1, the fracture is pure shear mode fracture, whereas gamma equals 0 corresponds to pure tensile mode fracture. A more detailed investigation of the hybrid model is a topic of ongoing study. Thank you.
Thank you very much for your presentation. Any question from the audience? No one? I have just an observation on the slide that you are sharing now. I see the first alloy, aluminum 2024, yes, with an heat treatment named T351. Omega is the strength of the material. 704.
No, that's the strength coefficient.
It's a coefficient.
For, yeah, yes.
It's not power, the resistance.
No. That's for power hardening
okay.
law.
It's the power of the relation.
Yes, that's the strength coefficient of when we use the power hardening law. So I use power hardening law, and that's the strength coefficient, and this is the hardening, and is the hardening exponent.
Okay, it's a coefficient because the in terms of strength seems to be too high.
Yes,
it's accuracy. My question is, why do you compare so much different materials? You use aluminum alloy in the STM steels up to easy 1035 steel. Seems to be all the investigated material characterized by a cubic face-centered one.
So the reason I investigated this material because I obtained the experimental data from the literature from Zhu and Engelbert's article. Yeah, that's the reason. Yes. So these were the data I was able to obtain.
I see the model works very well. It's my suggestion seems to be lied to the particular microstructure of these materials.
Okay. So would you have a specific material suggestion?
Because seems to be characterized by the same lattice.
True.
Okay.
Thank you.
Other question from the audience? No one? Thank you, Kostas, for your presentation.
Thank you. Thank you.
Mr. Chair, Mr. Chair, excuse me, your mic is closed.
I'm sorry.
No problem, no problem.
Okay. Thank you for the advice. Next presentation is entitled A Preliminary Application of a Machine Learning Model for the Prediction of Low Variation in Three-Point Bending Tests based on the acoustic emission signals from Kaklis, Saubi, Jamisora, and Adjutantis.
Good morning. Could you hear me?
Yes.
Okay. Let me share my screen, please.
Okay. Okay, we can see. Well,
Thank you, Mr. Chair. Thank you, Mr. Chair. Hello, everyone, and welcome to our presentation on a preliminary application of a machine learning model for the prediction of load variation in three-point bending tests based on acoustic emission signals. The present study was motivated by previous research experimental studies conducted by the same research group, where 6 three-point bending tests were performed on beams of Nestos marble. These previous studies have shown that the acoustic emission signal generation increases rapidly for loads exceeding 75% of the maximum load, while less than 20% of the total acoustic emission activity was recorded for loads up to 75% of the maximum load. We have introduced the terms critical acoustic emission level for the 20% of the total acoustic emission activity, and the critical load level for the 75% of the maximum load. The main idea was to investigate the application of machine learning techniques to predict the load variation in three-point bending tests based only on acoustic emission amplitude signals, and to interpret the slope of the cumulative amplitude versus predicted load curve as a potential useful tool for determining the forthcoming specimen. This table summarizes the mean value and the average value and the standard deviation of the fracture load and the maximum average cumulative amplitude. Based on the average values, the critical load level is 0.9 kilonewtons and the critical acoustic emission level is 1,538 decibels. Note that the specimen number 9 was not included in these calculations because it will be used later to validate the proposed machine learning model. Several machine learning algorithms were applied. For model training and testing, 5 out of 6 three-point bending tests were used. Number 4, 5, 6, 7, and 8, while the other one, number 9, was used for validation. This table presents the results for each model and algorithm. It should be noted that all models present quite high prediction ability, but the artificial neural networks model 2 has the highest coefficient of determination value of 0.996 and the lowest root mean square error value of 0.022. Here we can see the relation between the predicted and the measured load values for specimen number 9, and the predictive ability of this proposed model for the three-point bending load is verified. The application of the proposed artificial neural networks model provides the predicted load time series for specimen number 9. Here we can see the variation of the average cumulative amplitude with respect to the predicted load up to several percentage levels of the maximum load. Here is the variation of the up to 60% level, 70% level, and 75% level, where we can observe that the predicted load value do not exceed the critical acoustic emission level. After this critical load level, a rapid increase of cumulative amplitude is presented, while the slope of this curve increases rapidly up to the 100% of the fracture load. And it's clearly shown that the proposed model can successfully predict the load variation in three-point bending tests. The main conclusion from this study is that during the three-point bending test, utilizing only the recorded acoustic emission amplitude signals, the critical load level could be identified and can be used as a failure index of the material. In the future, we plan to extend this study by applying the proposed methodology in some other laboratory experimental procedures. And as a field application, a properly designed artificial neural networks algorithm could predict the pillar or roof behavior failure in several underground openings based only on acoustic or seismic recorded signals. Thank you so much.
Thank you very much, Kostas. And some questions?
Yes, please.
No one from the audience? Just a curiosity, because I used in the past the neural network apply it to other kind of problems. It works very well. And I think mainly in linear and quasi-linear models, because if you have phenomena where you have a lot of discontinuity, you can derive the model in that point, singular point, and the linearization in necessary to create a power law and the other one. You have no derivative to do in the singular points. But in this case, I have a curiosity. How do you eliminate the noise from the acoustic signal? You use the learning machine to eliminate the noisy, or you use a conventional filter?
No. This. Thank you for your question, Prof. These experiments were executed before too many years when I was in the Technical University of Crete, maybe 6, 7, 8, or 8 years. I'm not sure.
Oh, okay.
The noise. We dealt with the noise by reducing the threshold.
Okay, you use the method changing the threshold in order to eliminate
the threshold. We tried to play with with several values from 50 decibels, the upper 50, and we concluded at around 32 or 33.
Yeah, this is one of these methods. Another one could be to take a lot of the measurement using the same experiment, okay, and generate an average values of all the experiment, because the noisy could be plus or minus, and the summation eliminates this variation.
Yeah, this is your comment is regarding the machine learning algorithm, right? Or
machine learning, it could be or directly from the instruments, because I know there are a lot of recording. We can take this subroutine in automatic manner in order to filter this kind of problem.
Okay,
anyway, it's a very interesting technology, because using just a sensor and recording machine, you can predict problems like broken or other problems in many fields.
I agree, Prof. But I think that this is probably is a very interesting issue in engineering, but without too many field applications.
Yeah,
this is the point. We are working, all of us, in the laboratory, but without any field applications. This is the point. Thank you so much.
Thank you to you, Kostas. No other questions from the audience? No one. Thank you, Kostas and Kostas. And next presentation is just a moment. It's investigation of pop in formation mechanisms in fracture toughness test of welded joint and improvement of acceptance criteria. Authors are Agi, Imai, and Kawabata. Hi, Torun. Can you hear me?
Yes, I am. Can you see the screen here?
Yes, perfectly.
Okay. Please. Okay, so I will start my presentation. My name is Toru Yagi from the University of Tokyo, and I will have a presentation about the popping formation mechanism and the improvement of the acceptance criteria. Okay, so pop-in is a small arrested brittle crack which occurs during a CTOD testing. And when pop-in is determined as a fracture, the fracture toughness of the material is calculated by the point A on the PVZ curve on the slide here. And when it is not, the fracture toughness is judged from the point B, which is over here. Oops, the video is starting. All right, it is a video clip of the CTOD testing. And right now, popping occurs and complete fracture. Okay, so according to the Willoughby study, before the driving force of the propagating crack is weakened by the reflected stress wave, which reflects at the lower jig. Therefore, a small crack which arises before the reflected stress wave approaches will arise in the real structure too. And the maximum affected crack length is 4% of the ligament, which corresponds to the 5% of load drop ratio. Okay, and because of the absence of a test specimen, which ensure pop-in and the difference of loading mode of CTOD test and the real structure, pop-in standard is said to be too conservative. Oh, sorry. What's going on here? Okay. And the objective of this study is to investigate the pop-in mechanism and the improvement of the standard. On the experiment chapter, we first prepare the specimen which can ensure the pop-in occurrence. We prepare a section nut specimen, which is a reproduction of the real world with the local brittle zone. And we also prepared, we will also prepare the surface nut specimen for reference. And here is what I did for the experiment. And it is very important to know that the tensile mode represents the real structure in this study. And here is a typical fracture test results. We show you the fracture surface and the PVC curve. And here's a summary. From the first data from the left, you can see the pop-in of CTOD test, which has a load drop ratio of 10% or more. And since there's no tensile test which the brittle crack propagated through, you can say that it is fine to set the load drop ratio of 10% as a new pop-in standard. And here, now let's move on to the analysis part. We conducted the FEM analysis to see the reflection of stress wave and the difference of loading mode between the CTOD test and the tensile test. We evaluated with normalized dynamic stress intensity factor, KD, which shows the gradient of the driving force of the crack. From the result, the driving force of a crack decreases rapidly when the crack velocity is high on the bending mode. We show it in this area. And on the other hand, on the tensile mode, the driving force of the crack is unchanged. And based on the Willoughby's theory, the driving force of the crack with lower velocity should decrease more rapidly. And since the result of the FM analysis is opposite, there's a possibility that the Willoughby theory is incorrect. Okay, so here we propose a new pop-in model. It consists of the superposition of KD obtained from the FM analysis, which I showed you before, and the K of a tunnel crack shape model. The K closure is the closing effect from the side ligament, which is the area surrounded by these blue lines. The K closure 1 is this area, and the K closure 2 is the area surrounded by this rectangle. And this value is very, the width of the local brittle zone can really affect this K closure model, K closure value. And the important assumption for the interpretation of the model calculation result is the difference of the minimum. And this comes from the theory of plastic strain. And for this study, we set the minimum crack velocity of bending mode as a 10 meters per sec, and the minimum crack velocity of the tensile mode, we said it is as 400 meters per sec. And here is a simulation result of proposed model. What I want to say here is that this proposed model could really explain the actual experiment. Okay, so here is the summary of this study. According to the novel experiments which induces pop-ins and the numerical model that is combined FM analysis and simplified SF calculation, it was revealed that the current requirement in major standards for pop-in judgment was too conservative. And we want to say that if the width of the local brittle zone is less than 2 millimeters, pop-in of less than 10% of the low drop ratio can be ignored. And we will propose this new criterion in this committee in future. And thanks for listening. That's it.
Thank you, Taro. Any questions from the audience? No one. So, Taro, I see in your work you affirmed that if the width of the LB zeta is less than 2 millimeters,
yes, right.
pop-in is less than 10% of the load drop and can be ignored. Why did you use this criterion? It's an hazardous or not? Ignore this kind of phenomena.
Okay, so what I want to ask me is why I propose this new model. Okay.
No, why you propose this criterion?
Okay, so
to ignore the. Okay, please.
Okay, so the previous study, I mean, the current standard is based on the Willoughby study, which is done in 1991, and it is the theory of the stress wave. So the reflected stress wave from the lower J will interfere with the propagating crack, and then the driving force of the crack will be decreased by the reflected stress wave. But from the FM analysis I conducted, we find out that the theory of the reflected stress wave is incorrect. I mean, it is very difficult to describe the FM result from the previous study. And that is why we propose a new model and of this model, the superposition of tunnel crack model. And what is very good about this new model is that it is, I mean, as I said before, this model can really explain the experimental result very well. I mean, from this results, you can see that the popping crack length is shorter when the loading mode is bending, and you can see, I mean, and also you can also see that the crack will be arrested when there is a local brittle zone, and the 2 millimeters. I mean, the number of 2 comes from the experiment. I mean, the new weld joints that we made, the local brittle zone width was 2 millimeters, and that is why I used 2 millimeters as a new proposed model. How about this?
Okay, and other questions from the audience? I have another curiosity due to the fact that you will propose your model to the ASTM standardization, I think, and no, ISO TC 164 committee in the future. So, and my question is, how do you measure easily the closure in the real joints?
Okay, so
because when you propose in the standard committee, sometimes often a question of colleagues is okay, but the model is useful or it's much more complicated.
Right. I understand you, but okay, so you're right. I mean, for this model applies to this particular situation.
Yeah.
I mean, right. So to propose this new model to the committees, I mean, I definitely have to brush up my model. So I mean, the answer here will be is that I will brush up my model more to make this model very useful to the real structures.
Okay, it's easily implemented in a FE model and in a FE software. How do you can measure the closure in real joints?
Right. Yeah,
which is the way to easily measure the closure of welded joints using the conventional methods.
Right. So yeah, I mean,
by X-ray, yeah.
Yeah, I mean, I have to think about that too. I mean, so as I said before, I mean, this model can apply to the particular type of the real joints. So yeah, I have to think about how to calculate the cake closure of the real structures. I mean, with the local brittle zone of I mean, several types of local brittle zone. I mean, I have to make a new model or brush up this model. So I mean, thank you for advice.
Thank you very much. I think you can use, for example, X-ray investigation in order to take the section of the welding joints. For example, this is a possibility. Or in terms of the design, you can design the correct geometry to be realized in real components. It depends. So, any questions from the audience? No one. Thank you very much, Toru.
Thank you, sir.
And we move to the last presentation for this section. The title is Investigation of the Statistical and Geometrical Size Effect on the Fatigue Strength of ENGJL 300 under consideration of the graphite morphology by Kansi, Kainak, and Kaufman. Okay, please.
Hello,
Axel.
everybody. Can you hear me?
Perfectly, Axel. Please.
Thank you very much. So, yeah, I want to give you a short summary of my work to the statistical and geometrical size effect of gray cast iron. And to the motivation, the design of large components in regard to the fatigue strength is based on a small scale specimen tests. And to enable a transfer to the component, we need to consider the statistical size effect. And the statistical size effect, you can see here 3 different specimens with a different volume. We call this volume here the highly stressed volume, so where the maximum stress occurs. And the larger the sample, the larger the volume, and therefore the amount and size of defects is increasing. And with an increasing amount of defects, the fatigue strength is decreasing. If we use specimens with notches, geometrical size effect needs to be considered as well, which is due to the stress gradient at the notch, which leads to a small support effect. So the aim is the investigation of the statistical and geometrical size effect to be able to transfer the fatigue strength from the small scale specimens to large scale components. And here we have the investigated material, which was based on a component and cast samples. you can see the chemical composition and the microstructure of the gray cast iron, and it was a graphite arrangement of type A, so A graphite. So both investigated materials were comparable to each other. Here we have the specimen geometries, 3 different specimens with unnotched and notched specimens with a very big difference in the highly stressed volume. The highly stressed volume was determined by FE simulation. Here you can see in this picture the colored area, the maximum stress up to or down to 90% of the maximum stress, and the black area is the area with stresses below 90%. The experiments were carried out on this electric resonance test rig with a constant sine amplitude. And here we have the results, the SN curves. In comparison, the large specimens and the small specimens. And we see that the large specimens have a higher fatigue strength compared to the small specimens. And this is something which is very contrary to other cast materials. If we use the nominal stress amplitude and calculate the local stress amplitude by multiplicating with the notch factor, we see here the results of the local stress amplitude for the notch specimen. Due to the high notch, we have a very high local stress amplitude. Here the result for the small unnotched specimen, and here the result for the large unnotched specimen. And we see here the very high large local stress amplitude due to superposition of the statistical and the geometrical size effect due to the notch. So we see here a big support effect in the notch of the material. And then we have a decrease and then an increase. And this increase to higher highly stressed volumes in the fatigue strength is something which, as I mentioned, we have not seen before, and we need more experiments to get more information for this phenomena. So, gray cast iron was investigated. We fatigued different specimens with different highly stressed volumes, and we saw an increase of the fatigue strength of the large specimen compared to the small specimens of 14 and 18%. And we've investigated that the notch specimens could bear a high maximum stress amplitude due to the good microsupport effect. Thank you very much, and I am interested about your questions.
Thank you, Axel. Any questions from the audience?
Yes, Mr. Chairman, I'm Davide Paulino, and
Oh,
I have
Davide.
one. Hi. Just a curiosity, and congratulations for the topic. I'm involved in size effect, statistical size effect in very high cycle fatigue, and I almost followed your procedure in my research. But indeed, your results are quite unexpected. And so I would like to ask you if you considered the size of the defect at the origin of the fatigue crack to try to understand which was the defect population that led to the fatigue failure in the different specimens that you analyzed it.
Actually, we didn't do this. I mean, we investigated the fracture surface, but it was very hard to locate the defect where the crack began.
So, okay. So it was difficult for you to understand the origin of the
Yes,
crack.
that's true. I mean, the material with a like a network of graphite lamellas, it's there can always be the start of the fracture because of the lamellas which serve as a inner notch. So
Yeah.
we don't know yet which or how the parameters of the graphite lamellas lead to a crack beginning. This is something we're investigating right now, but we need more time for this.
Okay, thanks. And if it's possible, Vittorio, I have another comment.
Yes, please. Yes, please.
You talked about statistical size effect. Indeed, probably I missed something. In your presentation, I saw only some curves. Are they related to a particular failure probability? Or are they the median? I don't see the scatter in your curves. So
okay, in this presentation, I didn't have the scatter band, but I have this in the other. Maybe I can show you.
Just to see the scatter of the experimental data.
Do you see the results here now?
No, just the last.
Okay. Can you see it now?
Yeah, I see something different right now.
Okay,
but
so
not
we have
the curves.
Not the SN curves. Okay. Maybe if I share this one.
Yeah. Okay. I can see. Okay.
So we have here the scatter band of 1.1 and 1.18 for the large samples, and the scatter band increases the smaller the highly stressed volume is. So when we go to the small unnotched specimens, we have 1.36 and 1.31, and the notched specimens it's even growing.
Yeah, just to understand, the blue point are for
red. We removed specimens from a component and from cast samples we made for the project, and the red ones are from the component, which is a gear box housing, and the blue ones from the cast samples. And due to the very similar microstructure and chemical composition, we used both for the analysis.
Okay, and you don't have a curve, a plot, an SN plot with all the points together for the different specimen shapes, just to compare them in a single graph.
No, unfortunately, I don't have, because
no problem.
Due to the high scatter band, it will be like a cloud of points.
I would like you to try to investigate if the difference is significant or not. Maybe the 14 or 18%, if the scatter band is quite high, maybe not relevant. Just check.
Yeah,
check.
I know what you mean, and we checked it, and it is relevant. So
okay.
Yeah.
Okay, it's something that we all together we have to investigate, since it's unexpected. Thank you very much.
Thank you for your question.
Thank you, Davide. You did the same. My curiosity, I would ask to Professor Kanzi. Just an information, I know that in the European standards, there is a movement to perform some other tests in order to arrive release of a European standard about in this case, ductile cast irons. But I think the next step could involve the lamellar gray cast irons. And this is a very interesting field because a lot of components will be made on this kind of material, and the scale effect is important in order to improve the safety of components of car or other important machine in all the European market. Okay.
Indeed. I mean, in this case, if we can really see that the larger the sample, the higher the fatigue strength, it is possible to maybe redesign some of the components because in terms of lightweight, so reduce the material because the fatigue strength is higher. Yeah. So
I well understand.
Yeah, we're doing more tests with even larger samples, and
yeah, sometimes we use manner of production of component which involve big sections due to the technology. You realize that the gray cast iron. And sometimes components are machined and the section have to be very, very thin. The differences of mechanical behavior is very high, and knows a model or the phenomena to bring in our software tool to design the components is important. It's really important. Thank you very much, Professor Kanzi. Any questions?
I'm no professor. I'm just
okay. I'm sorry. I'm sorry.
Scientist.
I'm sorry. And the other questions from the audience? No one. Thank you so much, Axel, and thank you to all the participants of this session. And the next session will start at 11 o'clock. And thank you again. See you. Bye. Bye at all.
Bye.
Well, good morning or good afternoon to all of you, wherever you are. And I hope you are enjoying a good weather wherever you are. Our first presentation has the title Influence of Electrical Modification on the Mechanical Properties of Carbon Epoxy Laminates. Is any of the author here? The author are Shamsi, Farahani, Hu, Zhang, E. Moreira. Is anybody here to present the paper? I do repeat, is anybody here to present the first paper? Maybe that there is somebody from Portugal that is presenting this paper. All the others are from China and should be late in the evening over there. Well, I don't hear anybody. And so we'll go to the next paper, next presentation by Tatiana Petriakova from Perm in Russia. Is Tatiana over there, ready to present the paper? Is an interesting paper on the influence of non-monotonic loads regimes on the Porte-Vin-Le Chatelier effect in the aluminium magnesium alloy. Experimental study by using the DIC technique. Well, we are not really lucky this morning. I see Dr. Musa that is ready to go on the next presentation. At least I see him, so probably. Are you ready, Dr. Musa?
Yes, Prof, I'm ready.
Okay, Dr. Musa will present fracture behavior of cracked small punch test specimens made of epoxy reinforced by hybrid nanoparticles, and the authors are from University of tell me, Dr. Musa, which is university?
Yeah, we are from Gaza University in Saudi Arabia, and the other two authors are from Egypt.
Okay, Saudi Arabia and Egypt. Okay, is a good weather over there?
Yeah, it's very hot, so.
Okay, please go on.
I was planning to come to Italy, so maybe next year.
Well, here we are enjoying good weather too.
Yeah, good for you.
I don't know about the temperature. Maybe it's a little bit hotter over there.
It's around 44 now.
Celsius? Well, no, we are at least 12 degrees below.
Oh my God. Oh, great. Good for you, Prof. Okay, let me share my screen with you and let me know if you now see my presentation. Prof, can you see the presentation now?
Yes, I can.
Okay, good. Hello, everyone. This is Dr. Said Musa from Jazan University in Saudi Arabia. It's my pleasure to start this session. I'm here to present with my friends, Prof. Amr Abdul Hadi and Prof. Hassam Salam from Egypt. Today, we are going to present about our study in fracture behavior of cracked small bunch test specimen made of epoxy reinforced by hybrid nanoparticles. So the main two objectives for our study was about to using the small bunch test, which was adopted to measure the tensile properties to the present nano composite. And the second objective was to study the effect of the presence of the pre-notch with different three-notch geometry. First, the single edge notch, the second, the straight bottom notch, and the circular bottom notch, and the small bunch test specimen, which was have been studied both numerically and experimentally. So here I'm showing the small bunch test or the fixture that we have manufactured and designed in our lab, which was containing of upper and lower die, and the specimen will be placed in this hole, and we apply the load from the top, and we are showing some of the fracture sample of the epoxy. The material that we use is the epoxy as the matrix, and we use two different nanoparticles, which are the aluminum oxide and silicon carbide. So for the main result and discussion, I'm here showing the experimental result that we got from this study. In this figure, in the left one, which is about the small bunch test load deflection curve, which we're showing all the composite that we have manufactured and tested. The first one, the upper one here, which is have no additive. The other one, which is start to we have 0.5, 1.5, and 3% of additive of the aluminum oxide. And as we can see, like as we increase the amount of additive, we start to the load start to decrease. However, there are some significant pop in that we have here for all the composite that had a reinforcement. The other for the right one figure, which is the maximum applied load for the with different nanoparticles, we try to see what is we calculated the deflection of the maximum force. We get it from the slope here, and we can tell like increasing the amount of nanoparticle or reinforcement lead to an increasement in the stiffness. Also here we did some calculation or measurement for the Young's modulus of various aluminum oxide nano additive concentration. And as we can see, as the additive increase, the Young's modulus start to decrease. So this is for the experimental part. For the simulation, we did the stress distribution around the crack front of the three different crack geometry, which is the single edge, the straight bottom notch, and we did the circular bottom notch. We obtained the normal stress and shear stress, and we can tell from all those curves that the circular bottom notch, which is a very constitutive, like a very good fitting with the experimental, and we can tell like it is uniformly around the notch, especially for the circular. While for the other, we can tell how it is looks like, especially for the normal stress and the shear stress. Here we're showing the site crack initiation and crack path for the single edge node. This is the upper face and this is the bottom face. The upper face will have a compressive, the lower one will have a tensile, and we start to decrease the ratio between the length of the crack and the diameter of the sample, and we can tell like how it is looks like when we increase it from the crack is coming here and here for this one, and this is the notch how it is looks like. So this is for the site crack initiating for the SPN, which is the single bottom notch. This is the notch, and when we applying the load, the crack start to go from all over the bottom sample. Before the end, this is the site crack initiating for the CPN, which is the bottom notch. with different, between the crack path and the thickness of the sample, and we can tell like how it is looks like between the notch and how it is we get the crack, especially here in this one. Finally, some conclusion we get it from this study that the addition of the aluminum oxide, or especially 2% of aluminum oxide nanoparticle to epoxy resin, was found to be the optimum ratio in the present work. Also, to generalize the small bunch test, the material dependent empirical constant can be predicted by equating the tensile strength measured from the SPT and the indirect tension test. Also, the circular bottom notch specimen is a suitable candidate to determine the fracture toughness of the material due to its position coincides with the failure location of the SPT specimen. Finally, the sensitivity of the circular bottom notch is dependent on the, the length of the crack and to the ratio or the thickness, and the ratio of the circumferential of the circular notch to that of the loading pole. That's all. And sorry, I was in hurry, but I have just only 2 minutes. And thank you.
Don't worry, don't worry. We have been reading some of the work of your work before. First of all, I am asking the far away audience if anybody wants to step in and pose a question to Dr. Musa. If not, I would like to ask Dr. Musa to further rationalize, if he can, about the pop-ins, to which kind of phenomenon they correspond, some splitting, something.
Okay, Prof. First of all, the material that we used was about like using epoxy with different nanoparticle. This presentation is just only a little. We have done a lot of work using the small punch test, which is a very good. It's like nowadays one of the good technique that we started to use in our lab. So we tested different kind of material. The main, obstacle that we always face is how to simulate the SPT or the small bunch test using the virtual crack closing technique. We struggle how we do this. This simulation, and at the end we got some result. This is still preliminary result, but in the future work we start to do more testing, how we can verify between the experimental and the simulation.
Okay, okay. And when you say that there is a sensitivity in the bottom crack, there is a sensitivity to the ratio between the ball and the dimension of the crack. Can you further rationalize on that?
Yeah, exactly, Prof. So in this one, as we can tell here, like for the experimental part, we did this one. The ratio, the 0.2 and 0.5, and we got the same result what we got here. While we let me show you here this one. While we did for the straight bottom and the single bottom, we can tell like how it is react to the stresses for the normal stress and the shear stress. While for the circular, we start to see like it is a very it's a uniform, and it's a very close to what we got in the experimental part. So we did the notch for the experimental in the bottom, and we apply the load, and we get the same very close same cracks how which we get here for the circular bottom notch.
Okay, thank you very much.
It's my pleasure.
And I do repeat my question. Is anybody that wants to pose other questions to Dr. Musa? I don't think anybody waving the hand or unmute his microphone, and so I thank once more Dr. Musa.
Thank you.
And then we can pass to the next presentation, which is going to be about microstructural characterization of an ancient iron bridge in Brazil. There are many authors: Oliveira, Pardal, Correira, Arayu, Benini, Tavares, and Berto, our current president of IGF. So who is the one that wants to step in? Miss Better Doctor Lara Grip Oliveira, and please, the word is to you.
Thank you. So my work is out. Oops. So the title of the work is Microstructure Characterization of an Ancient Iron Bridge in Brazil. I am a PhD student from Brazil, and I will show you the main topics of the work. So here we study this ancient material from this ancient bridge from the 19th century in Brazil. It was initially built as a railway bridge, but today it is also used as a car crossing bridge. And just like this structure, we have many structures all over the world made with the same type of ancient material that was projected to one reason, but nowadays it is also used for different purposes. So our main motivation here was to understand the behavior of the microstructure of this material and how it can influence on the mechanical properties that we find in literature in order to have more information of how this material behaves to guarantee the structural safety of those structures that we are still using today. It is also known that these materials suffer a degradation process during time, so it's really important to understand and have more knowledge about it. So here we analyze samples from two different profiles, profile P1 and profile P2, and we made different analysis. So we started with chemical composition analysis of both profiles. We made a thermodynamic analysis. This is a simulation using the software Thermocalc, where we could analyze the precipitates inside this material and the chemical composition of it. We also analyze it by light optical microscope. Here we quantify the inclusions inside this material, and we also analyze the grain size and the shape of the inclusions. We also use the scanning electron microscope to analyze the inclusions, the slag inclusions that this material have. And we use the energy dispersive spectroscopy to analyze the chemical compositions of them. And in the end, we use the computer microtomography to analyze the distribution of those inclusions inside the material. Here on the presentation, we have the results for each of them. So this material has a low amount of carbon and high amount of elements that we don't desire nowadays, like phosphorus, sulfur, nitrogen. And these are characteristics of a specific material called podo iron. So here we have the results of the thermodynamic analysis, images that we obtained by the other analysis, transverse direction, longitudinal direction. There is difference, especially on the inclusions, the shape of the inclusions. On the longitudinal direction, lamination direction, the inclusions are more elongated. On the transverse directions, they are more round. And we have those big slag inclusions made with different non-metallic compounds, also a characteristics of the podo iron. We have ghost structures that is because of the heterogeneous distribution of phosphorus inside the matrix of the material. We have high amount of inclusions, around 5.2, 5.8% of the material, which is in accordance with literature. We have a high dispersity between the grain size and a big grain size. This is the G grain size of the standard ASTM. Here we have more images of the slag inclusions, the grain size. We also have these characteristics of the Newman bands on this material. More inclusions and fine precipitates inside the material. I will go. Here is the computer microtomography results. We can see the 3D shape of the samples that we use and the distribution of the inclusions inside of it. So let me go to the conclusions. Okay, so with the chemical compositions and the images we analyzed with the optical microscope, we could identify this material as a podal iron. This material has specific characteristics. There is a high amount of inclusions and a high amount of elements like phosphorus, sulfur, and nitrogen. With the thermodynamic analysis, we identified a high amount of precipitates rich in nitrogen and phosphorus, which is in accordance with the previous analysis, and how it can impact on the mechanical properties. Both those elements, they can influence on the properties of hardness and tensile strength, especially by the precipitation hardness. And because they are brittle elements, so this material have a high hardness despite the low carbon amount that it presents. So it's because of the influence of those elements. With the scanning electron microscope, we could identify that those inclusions are rich in phosphorus and sulfur, again, which is in accordance with the chemical composition that we obtain. And with the computer microtomography, you could see the distribution of those inclusions. It's a non-homogeneous distribution, and it has a high impact on the anisotropy of this material. This material has a high anisotropy, which has an impact on the impact resistance. On literature, we find that when we analyze samples from the longitudinal and transverse directions, the values we obtain are quite different, and also has an impact on the strain of this material. And here I give some future works like heat treatments, where we can try to minimize the influence of those precipitates and try to evaluate the degradation process and how it impacts on the mechanical properties of it, to analyze those fine intragranular and intergranular precipitates that we can see on some images by the scanning electron microscope, and also characterize the microstructure of this type of material using non-destructive techniques, because we will not always be able to remove samples of those structures. So try to characterize it with non-destructive techniques would be interesting. Basically, that's it.
Thank you very much. And I ask if anybody wants to ask a question to Miss Yara.
Yeah.
If not, I would like to ask questions.
Okay.
First of all, this is a powdered iron, I understand.
Yeah.
But where was the original ore mined? In Brazil? In which part of Brazil? The ores, ferrous ores, were obtained before?
We don't have the information, this information. The bridge is in Rio de Janeiro, in the state of Rio de Janeiro, but we don't have the information of where it was manufactured, the origin of the material.
Yeah. Because it seems from the chemical analysis results that you have an iron ore that is both high in phosphorus,
yes,
or sulfur.
Yeah.
And, in essence, you cannot do anything to improve the situation. Do you have temperature variations very large during winter and summer?
No.
No.
Not here in Brazil, no. Yeah.
No, but in that particular, I'm not speaking of the south of Brazil. This is, you said, Rio de Janeiro area.
Yeah.
So the variation shouldn't be very high, it should be around 20, 30 degrees
Yes.
of temperature. And can you tell us at least some value of the impact absorbed energy of this material? You are proposing to do some work on mechanical. And can you tell us which is the value of impact absorbed energy?
Yeah, on the longitudinal directions, we have values between 20 joules. But on the transverse directions, we find values of 6, 7 joules.
Okay, so you have that type of anisotropy.
Yes.
And 20 joule is really a low
Yes.
value of what we call in Italy resilience.
Yes.
And okay, and have you seen any real damage on the bridge? Sorry, did you see any damage on the bridge, actual damage?
No. In fact, we studied this material, we received this material because the bridge was under some reparation process. So we received this material to study and understand, have more knowledge about it to make those reparation process.
Okay, okay. That's why I was saying that you can't do anything to maintain that bridge. It has no tendency to corrode, but it depends from the environment that you have in that region. If that is just humidity, you might get some rust, but not very much because your carbon value is very...
Yeah, they had some problems with welding.
Well, you do not have to weld. You have to
yeah.
You have to maintain the original bond.
But they tried to weld some parts and they had problems with it.
Yeah, because there is a lot of sulfur and a lot of...
Yeah.
So that's okay. Okay. Thank you.
Thank you.
And, enjoy your weather and look at this bridge, maintain as a piece of ancient work.
Thank you.
Okay, okay. I think that somebody waved the hand to tell that they missed the time, but the first presenter is here, I believe.
Hello, good morning.
Okay. The first presentation was influence of electrical modification on the mechanical properties of carbon epoxy laminates by Samchi, Farahani, Hu, Zhang, He, and Moreira. And are you in China?
No, we are in Portugal, but they are our
You are in Portugal, because
yeah.
this is the Portugal to China and China paper. Okay, Dr. Samchi, it's your turn now.
Thank you very much. Okay. Can you see my presentation? Oh, can you see my presentation?
I see.
Okay.
Go ahead. If you want to put in a presentation mode, you can.
Oh, sure.
Okay.
Okay. So you can see, right? Okay. So our work, as you mentioned, Professor, is regarding the rate dependency of the material, of composite material. We're going to talk about the motivation of the work, the project that we involved with between two partners from China and Portugal, and the material they developed, experimental procedures, the result and conclusion. Basically, as we are getting more and more composite involved in the primary structures of the aircraft, we are getting a lot of benefits in terms of higher payload and lighter structures. But the structures are now susceptible for lightning damage because they are low, they have a weak conductivity, and the aircraft are expected to be hit by lightning like around 1,000 to 10,000 hours of flight. So at the time, we had these metallic materials, which are perfectly fine, and we could dissipate a large electrical currents. But obviously, with the composites now, we need to add more solutions. And as you know, one of the major state-of-the-art solutions are metallic meshes. But there are some issues with that, and because of the extra weight, and it's difficult for them to apply to the complex structures. Now researchers are looking for new solutions, such as metallized fibers, wales, and incorporation of nano fillers. So the collaboration now, our collaboration with the Avocado Center is based on developing multifunctional composite material, which they're aiming to produce composites that have higher toughness values as well as higher electrical conductivity. And our goal is to characterize these materials at higher loading rates and to see what are their damage properties at higher loading rates. So we did a lot of experiments, and here I'm going to present one of the experiments that we currently concluded. So the material was, the technique is functionalized with Interlayer technology. Basically, they're using silver nano wires and interleaving into a nylon rail, and then incorporating into the carbon epoxy laminates. This way, they are increasing the toughness and also the electrical conductivity of these laminates. So the dynamic experiments we performed with the Hopkinson bar, we developed the tension version here. We're able to reach the strain rate from 100 to 1,000 in tension loading configuration. And here you can see our data acquisition system. We use high-speed data acquisition system. We use PC scope, and we always measure our experiment with a high-speed camera. So the view of our setup, dynamic setup, and on the left we can see the counting system we developed for laminates. Is really an important system because we are having a laminate of thickness of 0.75 to 0.8 millimeters. So it's really easy to damage these laminates by just excessive compressive loading. And we applied the loading velocity of around 9 meters per second, and we reached a strain rate of 180. At the same time, in order to study the rate dependency, we performed the same exact experiment, monitoring with the CCD camera to obtain the images, the IC images, and performed it in a MTS servo-hydraulic load frame in order to characterize it under low strain rate regime. And here you can see the static result and the IC map of the specimen. Basically, the modification that we performed, there is no rate dependence. There is no influence on the material. We only saw an 18% decline on the longitudinal tensile properties of this material. And here is the failure mode of the specimen. They all failed within the longitudinal direction by splitting along the loading direction, regardless of the modification or loading rate. And here is the footage of the event. Basically, it took around 80 microseconds for the specimen to break. That was, as I indicated, it was around 180, strain rate of 180. And the next is the rate dependency of the material. The dashed lines represent the high rate behavior of the material. The material is absolutely not rate dependent, as you can see.
that's because of the dominant influence of carbon fibers along the loading direction, because we're actually loading into this degree of fiber orientation, and the carbon fibers are known to be not rate dependent. And there is a degree of oscillation, and it's because of the degree of nonlinearity in the results, and it's because of the oscillation we saw from our experiments. And here's also the DIC map. And regarding it, I can conclude the experiment we performed with the contention bar with the DIC analysis. We developed the test fixture, and we observed that the functionalized interlayer technology lowers the longitudinal tensile modulus. Obviously, it increases the electrical conductivity, which wasn't the focus of the study. And yeah, the laminates weren't rate dependent. And yeah, we need to do further experiments regarding the other mechanical properties. Yeah, thank you.
Okay, many thanks. And I would ask if anybody in the audience wants to put questions. If not, I have a curiosity. So you are saying that by lightning striking an aircraft, there might be some modifications on the Hopkinson bar response. Can you further rationalize on that?
Sure. Sure. Basically, the first goal is to develop the electrically conductive composite, and eventually, because the applications are in aeronautic industry, they need to have certain standards, so they need to withstand into the impact damage. So we need to see any solution that should be incorporated into the primary structures of aircraft should have certain properties. So our goal is here to assess the mechanical properties that are developed by our partners. So basically, the mechanical properties in order to run the advanced crash simulations or develop the material model. And have what is the tools that we use to measure the material properties at higher loading rates.
Okay, thank you very much, and enjoy your time.
Thank you.
And weather in Portugal.
Thank you.
The next presentation is about numerical analysis of geometrical modification combinations of the tensile strength of tubular adhesive joints. The paper is by Rosas, Campillo, and Moreira, and I do see Dr. Campillo over there ready to speak. Please. It is not important to go very fast, because otherwise the audience doesn't really understand the words. Okay.
Okay, thank you, Mr. Chairman. Hello, everyone. I'm happy to be in this conference at IGF26. This work it was mainly carried out by a master student of mine, Marcelo Rosas, and myself, Raul Campillo, and Raul Moreira. We are the supervisors of this work. This work deals with the numerical analysis of geometrical modifications and the respective combinations in the tensile strength of tubular adhesive joints, knowing that adhesive joints are nowadays used in several different applications, including structural applications with excellent results and advantages to other types of joints. The main objective of this work is to study different geometric modifications in tubular adhesive joints loaded under tension. And we can see in this first figure to the left the geometry of the tubular adhesive joints. we have different geometrical parameters which were kept constant, but the main parameter that was varied during this work was the overlap length, or LO. All of the other parameters were left constant. And this type of tubular joint, it is an overlap joint. So we have one of the tube that enters the other one, and then we have an overlap region bonded with adhesive. So this is the bonded part with adhesive. The materials for these joints were aluminum adherents, the AW682, which is a high strength aluminum alloy with a failure strength under tension of about 320 megapascal. So it has a reasonable strength. And in this first slide of results, I give a short overview of the experimental results, which allowed us to validate the numerical technique that we used in this work, which were the cohesive zone models. In the graphic to the right, we can see the maximum load for different overlap lengths. So we considered an overlap length of 20 millimeters and an overlap length of 40 millimeters. We have the experimental data points, the ones without a dotted line, and then we have the results with a dotted line in between, which correspond to the numerical predictions by CCM modeling. The results are overall good. We can see a summary of the experimental results and the relative difference of the numerical simulations in the table. For the three adhesives that we considered in this work, we used the Heraldite AV138, which is a very brittle adhesive, although it is strong. We considered the Heraldite 2015, which is a less strong adhesive, but with 5% of strain to failure under tension. And then we consider the Sikaforce 7752, which is a polyurethane adhesive with the lowest strength between the three adhesives, but with the highest ductility. So we can see the experimental data, the maximum load in Newton, and we can see the numerical predictions by CCM modeling. I'm going to give more details about this technique in the next slide, but we can see here the relative difference of the numerical data compared to the experimental. And we can see that apart from the Sikaforce adhesive, we have very good predictions. For the Sikaforce adhesive, we had some other predictions by the numerical models, but this is related to the very large ductility of this adhesive, which is not very accurately accounted for in the numerical model and the cohesive law that we selected for this work. But nonetheless, we can have a rough prediction with a maximum error of less than 20%. In this next and last slide, I give some details about the numerical work. We consider the Avocado software, which has an embedded formulation for cohesive elements, namely cohesive elements with a triangular damage law, in which after reaching the peak load, we have a linear softening up to failure of the CCM elements. In these models, of which I have an example here in this figure of the meshing process, we consider axisymmetric models, as we can see in this sketch to the left, in which we see the vertical axis of revolution of the model and the loading and the boundary conditions. So these are 2D models that replicate the three-dimensional axisymmetric shape of the tubular joints. Regarding the boundary conditions, we clamped one of the edges of the tubular joint and we applied a tensile displacement in the other, so as to emulate the real testing conditions in this type of joints under tension. Regarding the elements, we considered axisymmetric solid elements for the adherence. The reference from Avocado is CAX4, which means that the elements have 4 nodes. And we considered also 4-node axisymmetric CCM elements for the adhesive to simulate failure along the adhesive path. And in this case, the reference from Avocado is COH AX4. we consider different types of geometric modifications, which I don't have time to show here all of the results, but we consider mainly 3 geometric modifications: an adhesive fillet at the edge of the adhesive. So for example, this figure that we have here, this is a combination geometry. We combine an adhesive fillet with an inner chamfer. We can see here the edge of the outer adherent. This is an adhesive fillet with an angle of 7.5 degrees. So this is adhesive, this part. This is one of the modifications that we tested. Other modification was an inner chamfer of the adherent. For example, this figure here also has an inner chamfer. We can see here by the mesh topology. So this is an inner chamfer. So this part is not metal, it's not aluminum. This is adhesive. The aluminum part is here. And we also considered an outer chamfer. The outer chamfer, in terms of geometry, is very similar to the adhesive fillet, but we have the overlap length until this edge, and we have here an outer fillet of adhesive. And for the 3 cases, the main objective of these modifications is to alter the stress distributions so that we have less peak concentrations, and we have eventually an increase in the joint strength of the tubular joints. Regarding the results obtained for the adhesive fillet, we concluded that the maximum load increased by putting an adhesive fillet, and the strength is higher with smaller fillet angles. And the best results were found for the ductile Sika Force 7752 adhesive, up to a difference of 15% compared to the joint without geometric modifications. For the outer chamfer, the results were not so good, but we also managed to achieve strength improvements up to 10%. And in this case, the best results were also obtained for the Sika Force 7752. On the other hand, for the inner chamfer, we saw that this parameter has a marginal effect on the joint strength, disregarding the type of adhesive that we considered. After having these results, we tried to combine different geometric modifications, combinations. We could not combine the outer chamfer with the other 2 geometric modifications, but we tried to combine an adhesive fillet with an inner chamfer, and this is the example that we have here in this figure. However, since the inner chamfer did not show to have a very positive effect on the joint strength, it was found that the results were very, very similar to the ones obtained just using an adhesive fillet. So with this work, we tried to propose different geometric modifications. We saw that the adhesive fillet and the inner chamfer had some effect and can be used in design of this type of joints, so that we can have real strength improvements over the unmodified joints. So this concludes my short presentation. I am available if anyone has any question. I'm very happy to answer. Thank you.
So you will be happy if somebody asks you a question?
Yes, exactly.
Is anybody in the audience that raises the hand? Well, I don't see anybody really unmuting the microphone. I'm asking you a question.
Yes, please.
I understand that the larger the overlap, the best are the results. You are increasing the maximum load.
Exactly.
But from the economic viewpoint, is any influence in costs by enlarging the overlapping?
Well, economically speaking, in terms of fabrication of the experimental joints, regarding the geometry of the adherents, I don't think there is. I think we have a higher cost if we consider the economies of scale and by spending more adhesive. But I think that is the only inconvenient in increasing the overlap length. Actually, this is one of the geometrical modifications, if not the most important, that affect the joint strength. But I think it doesn't have a big much influence on the cost.
Okay, I understand it. So there is no economic advantage in reducing the overlapping. No
Yes.
real economic advantage. Okay, Dr. Campillo, are you presenting also the other three, or is anybody else presenting?
They are colleagues of mine, which are also in this talk.
Okay, so the next presentation is meshless approach to material plasticity in adhesive joints, and we have Resende and Resende, two different Resendes, Sanchez Haas, Ramayo, Campillo, and Bellinia, and Isidro de Jesus Sanchez Haas is going to present the paper.
Yes,
okay. Go ahead.
Okay. Hello, everyone. Thank you for your time. My name is Isidro Sanchez. I am going to present part of our work related to meshless methods and applied to analyzing adhesive joints. In this case, is meshless approach to material plasticity in adhesive joints. First of all, the common technique or the common numerical technique for analyzing adhesive joints is finite element method, which is easy to obtain, is commercially available, etc. However, meshless methods have some advantages, mainly for complex joints, complex geometries. The only inconvenience of meshless methods is that they are still in development. In consequence, we don't have only a meshless method like the FEM. We have perhaps 20, 25 different meshless methods around the literature, and none of them is available commercially. Anyway, besides that, the techniques for analyzing adhesive joints from the theoretical or analytical that are based mainly in closed form equations are based in elastic models, elastic adhesive, elastic adherence. In the case of the finite element modeling, using elastoplastic models is more or less straightforward until we arrive to the next point. It's quite common in the literature to use the von Mises yield criterion for analyzing adhesive joints, which is acceptable up to a certain point, mainly for brittle or adhesives with low ductility. In our case, upon some literature review and after some problems found with ductile adhesives, we decide to implement the exponent Drucker-Prager yield criteria into a meshless method. In this case, we're using an interpolation method. Is the radial point interpolation meshless method. Is not a new method. It has been around for perhaps 18 to 20 years. However, this method in particular has the advantage that it's quite accurate, is quite well spread in the literature. Therefore, what we do here can be easily applied for other research groups around the world, in contrary to more recent meshless methods that are quite particular to some research groups. Anyway, the difference between the von Mises yield criteria that is ubiquitous and the exponent Drucker-Prager is that the exponent Drucker-Prager takes in account the compression of the adhesive during the load, and therefore being sensitive to the hydrostatic pressure, the adhesive can modify, or the model takes into account the modification of the yield point. So here we have the surface of the exponent Drucker-Prager. In this case, is a paraboloid. If we compare that with the von Mises is just a cylinder in the space. This would be the von Mises. Anyway, in tensile, if we apply more hydrostatic pressure, our yield point will reduce. But if it's compressed, our yield point will increase. Therefore, our joint strength would be changed. The equation is rather simple. It takes into account the deviatoric or the equivalent or the effective stress, like when calculated with the von Mises equation, and takes into account a quite interesting parameter, lambda. This parameter is not available in the literature, and let alone for all the adhesives. So this parameter has to be calculated for every adhesive. It's necessary to perform tests in two different directions. So in this case, we're using tensile testing and shear testing, but it can be shear and tensile, shear and compression, tensile and compression, a combination of them. This parameter is just to relate how the yield surface is changing. So once the parameter is taken care of, it's also well known that if the parameter goes below the square root of 2, it's not necessary to use this equation. We can go to the von Mises equation. And one of the things we implemented with this methodology is the ability to switch from one criteria to another just by playing this by modifying this parameter. So if the parameter is equal to 1, this equation takes the form of the well-known von Mises equation. If the parameter goes beyond that, it takes into account the exponent Drucker-Prager criterion. Sorry. What is important for us? As the adhesive joints we're analyzing are composed of aluminum and adhesive, the aluminum certainly yields using the von Mises criteria. Entonces, therefore, we use this approach to take into account both materials. Okay, how it was implemented. The meshless method itself, I'm not going to explain it here because it's out of the scope. However, we have been working in this for a few years now. I can explain in little, very small, that this meshless method, what it does is taking in account a set of 16 Gauss points around a node and interpolates the coordinates of 16 nodes around every Gauss point. So interpolates the position of them or the force or whatever. And it is kind of sweeping all the domain. So in this case, instead of a finite element with 3 or 4 nodes, we have a moving element that is having up to 16 points is the difference. Besides that, the application of boundary conditions, loads is quite similar, as well as the solution. So it just takes more time. For testing the implementation, we use a single lap joint bonded with aluminum, the series 6000. We tested 4 overlap lengths and 3 different adhesives. 2 of them are similar to the ones presented before. and the other one is a quite ductile and tough Sika 47888. And the results were evaluated using both criteria, the von Mises and the Drucker prior. Once we did the solution, we wanted to compare what happened if we run the cases using the von Mises and what happened if we run the cases using the Drucker prior. So here in the very left, we have the P delta, the strength prediction for the AB138. And we can see that for overlaps from 25 millimeters up to 50, the numerical predictions are quite close to the experimental as expected. However, for the lower overlaps, it tends to overpredict. Is something that we expected because this adhesive is brittle. So sometimes the model doesn't fit. It's something that it has been observed in the literature. But we know, in fact, that for 12.5 millimeters, even with a linear elastic model, it can be, even with analytical model, we can get pretty good results. So that's not a problem. However, for the Araldite 2015, we can see our predictions got better. Although they are more variable, we are close to the experimental data and close to other solutions, the CCM, which is very well known in the literature. It can be seen as well that the exponent Drucker-Prager is always providing slightly higher strength values compared to the von Mises. However, for the 37.5 and the 50 millimeter cases, our strengths are a little bit below, up to sometimes 20% in the larger overlaps. There is, I will explain this in the next slide, because it depends of the failure criteria chosen. So it's not a problem of the method. It's more or less related to the analysis. Anyway, for the 7888, we have the same behavior. However, this adhesive is very ductile and tough, so the results get a little bit lower. It is expected. In consequence, we need to implement further techniques to the method in order to make it improve. Here we compare the stress distributions. In this case, is shear between the two criteria. It can be seen that the patterns are similar for the smallest overlaps. However, it changes in the larger overlaps. Why is this happening? Because of the compression in the center of the overlap. So the Drucker-Prager criteria is taking into account that this part, this U-shaped part, hasn't yield yet. So, or haven't reached a certain level of plasticization. So for that reason, the curve is different. We can see as well that the stresses are a little bit lower using the von Mises criteria. It's expected. This difference in stresses is what causes the difference in the strength prediction. The other thing that causes the difference before is we chose a unified failure criteria for all the adhesive, for all the overlaps per adhesive. It can be used an individual failure criteria for every adhesive, for every case, as suggested by Hart and Smith in the 70s. It can be done, and it will improve much more the results. In conclusion, as we increase the overlap length with this criteria, we find that the adhesive layer is not plasticizing, therefore we can sustain more load. There is a direct change in the stress distribution because of the yield criteria, the yield criteria. However, it accounts for the prediction of the strength. And we can say that the Drucker-Prager criteria, exponent Drucker-Prager criteria predicts higher joint strengths in comparison to the von Mises. And these predictions are closer to the other numerical techniques that are more well known in the literature. For my side is everything. Any question?
Just a very short one because we are a little late. You were saying that of the three adhesive that you were using, one was brittle, the other was ductile, and the one, the 2015, was in the middle with some ductility. How do you define brittle or ductile? On the basis of what?
Okay, we can say that an adhesive is brittle if the failure strain is below, if I remember well, 2%. That is defined in the literature. The EV138, the failure strain is 1.2%, if I remember well. The 2015 is ductile, which its failure strain is 4%, 4.7, and according to literature, it can be considered ductile if the failure strain is below 10, 15%. And finally, the 7888, it has a failure strain of 43%. So this is quite ductile.
Thank you very much.
You're welcome.
And then we pass to the next presenter, which I believe is Ricardo Rocha. Is that so? Unmute your microphone. Impact loading analysis of tubular adhesive joints, and Silva, Perez, Campillo, and Rocha are the authors, and Ricardo Rocha is going to speak now. Ricardo?
Hello, good morning.
Yes, you can do.
Hello, can you hear me?
Yes, I can.
Hello?
Yes, I can.
Okay, my connection is a mess. So, good morning.
If you want, I can raise my
I
voice
am
even
Ricardo
more.
Rocha, and I'm at my office, so I will try to speak a little bit louder. Can you hear me better now?
Yes, yes, yes. Go ahead because we are late.
Okay, I am Ricardo. I'm a researcher at INEGI, and this is my presentation: impact loading analysis of tubular adhesive joints. So the main objectives here is the application of CCM method for strength prediction of tubular adhesive joints under impact loading, validation of experimental and numerical data, and the evaluation of the main parameters to select the optimum geometry. Okay, since many of the principles that rule lap joints are also applicable to tubular joints, we used data from the literature to validate our model. So we select a single lap joint subjected to impact loads, and we compare our model with the experimental and numerical results from that reference. Sorry. So as you can see, only the last adhesive, that is a 6852, it's an hybrid adhesive, shows a large scattered data than the others, with a 50% of overestimation compared with experimental results. Well, this can be explained because sometimes it's very hard to reproduce numeric experimental data on a numerical work, and some issues can be attributed to imperfections in the joint fabrication, load cell accuracy, and possible misalignments in the testing machine. Nevertheless, we consider our model validated, since for AV138 and 8005 we attain good results. With the numerical model validation, we proceed to our objective, that is to
We are having
evaluate
problems. Sorry,
changes in
Ricardo. We are
the
Ricardo. We are having problems in hearing you. Your
in
voice
the
comes and goes.
overlap, fillet, adherent thickness. Yes.
I am having some problems in hearing you because your voice goes.
Hello, it's better now.
Yes, it is. Okay.
I'm going to stop the video. It might help us a little bit. So continuing in my presentation, after the numerical model, that is to change several geometrical parameters and evaluate which is the most suitable for
We have lost you, Ricardo. We lost you. Is anybody that can help in place of Ricardo?
Yes, Mr. Chairman, I can talk a little bit
Yes.
if I still have time. Let me just share the presentation, please. I am about to share. I just have the complete version of this work, but I will just make a short remark if it is possible.
Yes.
Well, so in this work we tested the tubular adhesive joints, we made a validation, and we tested different different geometric modifications of the tubular joints under impact loadings. We could see that we had major strength improvements over the joint without geometrical modifications. For example, if we see the first figure, by considering an adhesive fillet with 15 degrees of angle, we managed a 58% increase in the tubular joint strength under impact compared to the joint without modifications, which is the blue column. For the DP8005, we also had good strength improvements with adhesive fillet and adherent thickness. And finally, for the ductile and tough hybrid adhesive, the XNR6852, we had also a good strength improvement, but in this case, only 34%. As a main conclusion, we managed to validate the CZM technique adapted to impact loading by considering properties that are adjusted to the impact loading scenario. And we provided these design guidelines, these geometrical modifications that allowed us to use in the design process of these joints. I think that this was the main issue of this work, the main topic.
Okay. Which kind of spring steel were you using? Because I'm not familiar with the DIN. It's a silicon 7.
Yes. This is the steel that we use just for the validation work, the validation with single up joints, and it is a spring steel with high strength, with a yield stress of over 1 gigapascal, because we did not want to plasticize the adherents so that it would affect our results. So we wanted to have damage concentrated only in the adhesive layer.
Okay, Thank you very much.
Thank you.
We can thank you, Dr. Campillo, for stepping in impromptu, I would say in Latin.
You're welcome. It's a pleasure.
Okay, now we go to the next presentation, meshless and hyperelastic implementation to analyze flexible adhesives by Sanchez Arce, Gonsalves, Ramayo, Campillo, and Bellinia. Who is going to speak now? Isidro, thank
Yes,
you very
doctor.
much.
Can I share the screen?
Dr. Campillo, can you switch off your screen? Thank you. Thank you.
Okay.
Everything is okay now.
Okay.
Isidro, it's up to you.
Hello again. Just for some reason now the screen is behaving weirdly, but okay. I will present this way. It's better for me. Hello, everyone. My name is Isidro Sanchez again. I am going to present part of our work. In this case is meshless and hyperelastic implementation to analyze meshless adhesives. This work is a work developed by a team composed by Diego González, Luis Ramalho, Professor Campillo, Professor George Bellinia, and myself. Why implementing hyperelastic models? As we have been presenting the last three sessions, not all the adhesives have the same mechanical behavior. So, for example, there are brittle, there are ductile, tough. However, some of the adhesives that are ductile, they cannot be considered fully elastoplastic. Therefore, we found that it is necessary to analyze them as hyperelastic. That part is not well studied in the literature. There are very few applications of hyperelasticity to adhesive joints, to adhesives in general. Some of them are from the National Physics Laboratory in England, and they are 10, 15 years ago, and a couple of random ones. Then, if we step to the meshless approach, we got into more troubles because there are one or two works, and again, differing the meshless method. But anyway, from this, there are, we know that there are many hyperelastic models from the Treloar in 1944 until the more recent. The most popular ones are the Muni-Rivlin, the Treloar, or also known as Nehookian, the Ogden model, the Yo, which are the most used for adhesives. Anyway, here in this work, we wanted to implement a model that can take in account at least 2 or 3 hyperelastic models. Why? Because as we work with a variety of adhesives, it's necessary to have a better choice without the hassle of making 3, 4, or 5 different numerical cases. So in this case, we chose the Ogden model. As we can see in this slide, all of them are represented as a function of the principal stretches of the strain tensor. So doing this approach and implementing only the Ogden model, we can model the Nehookian and the Muni-Rivlin just by adjusting the constants. Therefore, it's easy to implement and easy to apply. There is, however, this model, the Yo model, that is more recent, is an extension of the Nehookian model, just it's kind of an exponential part version of it. However, once this Ogden model is working, it's easy or easy enough to implement the Yo model. So that's for future. Anyway, We implemented the octane model into another meshless method, the NNRP. Is similar to the one I presented before. The only difference that this one doesn't require a background mesh. This one only requires the nodes, and from that we create everything, which is more meshless than the other. But this is a little variation. The questions are the same. So we tested two numerical cases to see if the implementation was working. The first one is a little plate, 2 by 2 meters with Muni Rivlin parameters. The material parameters were taken from literature, from the work of Kosropur in 2019. And we created the nodal distribution, this second plot, and the nodal distribution together with the Gauss point distribution. We can see that this method in particular creates a lot of Gauss points, which
Isidro, if you go on presentation mode, we see better and you have to work less.
Okay.
Presentation mode.
Okay, I will go quicker now. The second case is dog bone shape following the ISO 527. This one was using the material properties of the adhesive, of the 7752 from Sika Force. We run the simulations using the hyperelastic routine we implemented, and we compare force displacement curve for the square plate. We got differences below 2.1%, which is good compared with the Abaco solution. And we compare normal and shear stresses. I am presenting here the shear because it allowed me to see if there is a difference in the magnitude and in the pattern, and also if there is a problem with the polar decomposition during the implementation. And we can see that everything looks right, the magnitudes are right, even in the little excess concentration in the tip. The same applied for the dog bone shape specimen. Here I am presenting the normal stress and compare it with Abacus. In this case, with the dog bone shape, we have a difference between 8% in the force displacement curve. However, for the stresses, we are around 1% in difference with, compared to Abacus. In conclusion, these results obtained with the mesh methods are quite similar to those obtained with Abacus, which is a common, a well-known tool. The main difference is that with the meshless approach, we are using up to 14 times less nodes compared to the solution required for Abacus to get the similar results. So in conclusion, this implementation is working and is providing good results. For my part, is all. If you have any question.
Okay, any question from the audience, please? Well, if not, I wish you to proceed into this large program of simulations and experimental validations. And now we change continent, if I understand properly. Okay, you can take out your screen.
Thank you.
We go into a review porosity in aluminum welding. We have a contribution from Indonesia, I believe, and Rizki Dwi Ardika is going to present you. Repeat your name in proper words because my pronunciation is not the best one. Triono and Triono, another Triono, are co-authors of this work.
Is my slide visible, sir?
That's too much. Go back and okay, thank you. Okay.
Hello everyone, I am Rizky Dwi Ardika. I am studying 11 Maret University. I am from Indonesia. I am here to tell a little about my article and review porosity in aluminum welding. In modern time, aluminum is widely used in the automotive, railroad, and marine industries. Aluminum is widely used because it has the advantage of low density, heat strength, and corrosion resistance. Manufacture of marine vessel using a lot of aluminum. One of the ship welding process is to use welding techniques because it has heat strength, relatively fast processing, and low cost. Welding process that are often used are gas metal welding and gas tungsten welding. However, aluminum also has this disadvantage, namely the emergence of porosity. In the area of the weld joint, porosity is caused by the presence of hydrogen. What are porosity? Porosity defects are welding defects in the form of small holes in the welding part, either on the surface or inside. Porosity can cause a decrease in the strength of the welded joint. Porosity is caused by the presence of hydrogen solution. Next, on slide 3, there are some cards about porosity. The vis is the form of porosity. There are two forms of porosity, namely microporosity and macroporosity. In the image below is an example of macroporosity and microporosity. Another porosity image can be seen in the picture on the set. The second is the influence of the environment on porosity. The factor that influence porosity in welding are high temperature during welding and humidity. The third is the impact of porosity on the mechanical properties of welding. Reduce the effectiveness of the weld joint, decrease ductility of the weld joint, reduce fatigue stress, significantly reduce the strength of the weld joint. Maybe that's enough for my person. Thank you, sir.
Did you finish?
Yes.
Okay. I understand that there is a large influence of humidity in the amount of pores. And you are also saying that there is a solution of hydrogen into aluminum. I am not familiar with hydrogen into aluminum. I know that hydrogen in steel can reduce ductility and fatigue resistance. What about aluminum? Solution of hydrogen into aluminum. Does it reduce ductility as in steels? I don't know if I was enough clear. Okay, don't worry. I think that we have reached the end of our session, and I thank all the audience. I thank all the speakers. We were very successful. Only one Russian girl wasn't able to join us, and so I think this has been a great success. Enjoy your meal and be ready to come back at 2 o'clock Rome time for a session with Professor Carmina Maletta as a chairperson. Enjoy.